So, all right, let's go through. So we got a quiz. I've decided for sure the quiz will be Monday, not Friday. So we've got one new thing to talk about today in section 2.5. And then that's really it. I mean, the rest of the week is going to be just practice on all these different things. And, you know, giving you a chance. I've thrown a lot at you so far. I'm going to throw some more at you today. But then it's going to be a lot of, you know, making sure you're asking the questions you need and getting practice on these various things. So yesterday was about these derivative rules, adding to our derivative rules. And, of course, the antiderivative is just kind of working that backwards. Exponentials, logs, trig. Okay? And then we're going to, of course, the real emphasis then is being able to use those derivative rules, okay, for problems that are more meaningful. All right? So we got to practice the derivative rules a little bit. So we're going to be talking a lot about little hints and tricks that I can give you as far as your algebra and how you write things that can help you. Okay? The first thing I want to mention about number 6 is that they give you h of x, and they say find h prime of 1/10. Well, one thing you're going to hear me say a lot this year, until I at least figure out that you've caught on, is before you can find h prime of 1/10, you have to find h prime of x, right? Before you can find h prime of 1/10, you need to find h prime of x, because you've got to have something to plug the 1/10 into, right? So they ask for h prime of 1/10. I first have to do this, h prime of x. So the rule says for a log, I do 1 over x, and then I have to tack on a 1 over ln 10, whatever the base is, okay, which is a 10. That's my h prime of x. Now, to do h prime of 1/10, I just plug in a 1/10 everywhere I see an x, okay, which is right there. Now, I wouldn't leave it like that. I don't think you should. When we do chapter 3, where we do a lot of these derivative problems with all the rules that we end up with, I would not let you leave it like that. 1 over 1/10 is 10. Now, at that point, if you want to leave it like that, I'm fine. I think it's better to put the 10 on top and write it like that, but either one of those would be okay. Spencer. What do you mean? Okay. I'm glad you said that. Okay. Solve. The word solve is going to really have important meaning for us today, right? Is like solving an equation. So I think what you meant there, instead of solve, the better word would have been simplify, okay, or convert to a decimal, right? Now, I would suggest to you on this chapter, in this page, it was just like the other ones, that this is no calculator, right? To me, this problem would be no calculator. So without a calculator, you're not going to be able to make it, right? So, and here's the other thing. I think when you get an answer like this, and you change it to a decimal, you're just asking for trouble. Because you might type it wrong, you might round wrong, you might forget 3 decimal places, you see what I mean? Anytime you give a decimal answer, it's got to have 3 decimal places. So why bother typing that in and messing something up, right? So no, I don't necessarily care for decimals unless the problem specifically asks for it. Okay? All right. So then you had some other ones in there. Number 8 was kind of the same thing. All right, let's move on to number 16. These are some that I picked out. I picked out quite a few of them, so forgive me if you didn't have questions on these. But 16 was purposely given as a function to make you think about the rules. We're never going to see a function like this. You're never going to see x raised to the e. But it makes you think about the rules. Okay? The reason this problem was given is to really make you think about the difference between these two functions. What's a derivative of x cubed? Power rule. Bring the power down. Da, da, da. What's the derivative of this? They're two totally different functions, and they're two totally different rules. This is a power function. This is an exponential function. They're very different, totally different families of functions, totally different derivative rules. Okay? So, what's the derivative of e to the x? E to the x. What's the derivative of x raised to a number? Because e is 2.718.
That number times.
So you bring down that number, and then you drop the power by 1. Like that. Now again, we'll never, hardly ever see a function like that except maybe on a derivative test, but it forces you to think about the rule. Okay, and then plus, what's the derivative of e? 0. It's 2.718. It's a derivative of 2.718, which is 0. Okay?
When doing antiderivatives, do you always have to put plus c?
Yes.
Like when you take points off, not put plus c?
Depends. Usually not. But we will be getting into, actually today, some problems where part of what you have to do is find the c, right? So if you don't put the plus c, then that's going to throw off. So yes, you definitely can lose points for that. All right, so let's go on to, is it number 22 then, that was the second derivative for this one? So now we got to do the derivative again. Well, the derivative of e to the x is still e to the x. And then this is just like having 7x to the fifth. You got number setting in front. So what is the number setting in front? It just stays there, it just hangs out there, right? And you bring this power down and multiply it and drop that by 1. So the e is just going to sit there. The e minus 1 is going to come down. And now the new power is e minus 2. You drop it by another 1. So it's now e minus 2. Okay? And then, of course, 0 is, there's nothing there. Say it, yes.
If we simplify that to e squared minus e times,
It's fine.
that's fine.
To me, that's just kind of rearranging a little bit. It's, we're going to have a discussion, especially when we get to chapter 3, about what does simplifying mean, because it's not a real black and white answer, right? Is this simpler than this? To me, that's just kind of rearranging. I don't think it is simpler. So, but if you do it, that's fine. Okay. All right, and then 28, was it? Was the one you had to do the antiderivative? Okay, so now we're looking at the red one up here, and we're saying, what function must it have been that when you did the derivative of the one down here, you get that? That's how you think about antiderivative. So obviously it had to be e to the x. And then what about this one? Well, it had to be a power of what? It had to be e plus 1. It had to be 1 higher. So think of it like guess and check. Think of antiderivative like guess and check, if you're struggling with it at all. Think of it like guess and check. So let's say that's my guess. I think that's the derivative, or antiderivative. So let's check it. Let's do the derivative. So I would bring down an e plus 1. Oh, there's no e plus 1 there. So there must have been something setting here that when I brought down the e plus 1, it canceled it. So that'd be a 1 over e plus 1. And then when I bring that down and cancel that, then that's going to subtract by 1, which would be e, and sure enough, that'll work. And remember, 1 over e plus 1 is just a number. It would just hang out there. It would just be hanging out there. Okay. Plus, what's the antiderivative of e? Yeah, not e to the x, but e times x, because this is just like a 7. What's the antiderivative of 7? What's 7x? Because the derivative of 7x is 7. So this is just e times x. And then plus c. It's important that you make sure that looks like e times x and not e to the x, because that's what we sometimes put there. That's very different. Okay, and then don't forget the plus c. Okay? All right, antiderivatives are not going to be a big thing. If our next quiz is 30 to 40 points, there's going to maybe be a couple on antiderivatives, just some simple antiderivatives, 3 or 4 maybe, I don't know. Not a whole lot on that. More on derivatives. You're going to have to do derivatives a lot more than antiderivatives, right? We're doing some simple, what I would call, or basic, I guess I said yesterday, antiderivatives. Just kind of thinking of the derivatives in reverse. All right, then I want to talk about 18 just a little bit. Just because that had that ln e thing, just quickly, we talked about this yesterday, but 2 would just stay put. Here, you get its own derivative whenever you have an exponential, but you have to tack on an ln 3. Okay? Then it was number 24, I believe, where you had to do the second derivative. So, what I wanted to mention here is, when you have these two that are just numbers, it's probably a good idea to put those together around front, and then put the exponential at the back. It doesn't really matter. You could leave your answer like this. But when you're going to have to move on with it and work with it, like we're going to have to now as a second derivative, it can be good to rearrange how you write it. I'll show you that especially on the next problem, where that's really critical. But anyway, when I go to do this derivative, this is just a number now that's going to hang out in front. 2 ln 3, and now I'm going to do this derivative right here, which is just going to be that times another ln 3. I'd say leave it. If you want to put ln 3 all squared and put those together, fine, but not necessary. You know, if it was 3 times 3, I think you should put that together and make it 9. But ln 3 times ln 3, I'm not sure putting ln 3 squared is that big a deal, big of a change, so I would just leave it. Okay, let's do 30. So 30 was then the antiderivative, right? Well, you're wanting to get back to this. Well, you know a 2 is just going to hang out. And you know this thing's its own derivative, right? So a good guess, if we're going to guess and check, would be this. So you say, okay, let's just do the derivative of this. Well, there'd be a 2, yeah. It's its own derivative, yeah. And then you tack on an ln 3. Oh, there's no ln 3 there. So there must have been what?
1 over.
There must have been a 1 over ln 3 sitting here, because that's just a number that's multiplied, so it's just going to hang out. So this and this would just hang out. When you do the derivative of this, you get this, tack on an ln 3, that would cancel that. You would just have that there. And a plus c. Okay? And a plus c. Now, should you rearrange this? I don't care, right? You could bring this and this together as that. But if all you're doing is rearranging it for your final answer, I don't care. Doesn't matter. Okay, so either one of those would be okay. Now, I wanted to make a comment on number 20 then. I went ahead and did the derivative on number 20. 3 is just going to hang out. The rule for log is 1 over x, and then a 1 over ln 2 tacked on. Now, this looks a lot like this one did here. And I said you didn't have to rearrange that, but on this one, I need to now do the derivative. Well, this doesn't look like any of my derivative rules that I had. So rearranging it so you can do the derivative is really important, I think. So what I want to do is take this and put those together as this, and then my 1 over x would be x to the negative 1. Now that's a much better thing to do the derivative of, because what I have is a number just hanging out in front. So the 3 over ln 2 is just going to hang out there. And then now I'm just going to do this derivative. So I'll bring the negative 1 over here. So I'll just put it there. And then x to the negative 2. So how I write it really can make or break my derivative. How easy my derivative is to do. Okay, so you really got to get in the habit of writing it so it looks like one of our rules. Question? All right, let's go to 35 here real quick and talk about this one. Again, just talk about some notation things. So you have the population. So here's where we want to start being able to use these derivative rules. So you got the population of this town, and T is the years after 1960. So 0 would be 1960, and they want to know what's the population in 2000.
Why is it called boom? Rapidly.
It's sarcastic, I guess, right? It's irony. Would that be irony? So here's what I'd like you to get comfortable doing. This notation. If they give you a function p of t, and they tell you that t is the years after 1960, and they say, what is the population in year 40, or excuse me, in 2000, I want you to write this. I want to start seeing this on your paper. I'm not saying it'll be wrong if you don't, but I'm telling you that as we go through the year, it's going to make your life a lot easier if you get comfortable using that notation. It's going to tell you, just using good notation makes problems easier to do many times. Okay, it's just a little trick that could be good for you. So we're going to just plug in a 40. So you just get on your calculator. You know, it'd be good, to be honest, it would be good to get in the habit of actually writing this out, right, like that, because it really shows this is what you did. Now if you type it in wrong, see, because here's the thing, if this was worth like 2 points on a test, and you didn't write P of 40, you didn't write this out, all you did was go to your calculator, because you would have to use your calculator on this one, okay? If all you did was go to your calculator and type it in, you typed something in wrong, and all you had done was an answer, you'd probably lose both points. Because I don't know why you got the wrong answer, but if you wrote this, and you wrote this, and then you typed in your calculator wrong and got the wrong answer, you get 1 point, because I know you were doing some stuff right. Okay? What'd you get here? 22,000. 285, and I'd say it's people, so you'd probably not use decimal places there. Okay? Now, look at this. See what I've done there? It said, what is the rate of change on January 1st, 2000? Well, that's where you need to say and communicate to me that you understand they're wanting the derivative at 40. And like I said earlier today, before you can find P prime of 40, you need P prime of
T.
T. Right? We'll be using T a lot as our input variable today, actually, on the homework, as opposed to X. On exponential functions especially, because it uses time a lot. Okay? So I need P prime of T. So that would be 50,000, which would just hang out there, times 0.98 to the T, it's its own derivative, times ln of 0.98. Right? Because that's the rule. You got a number just sitting out in front, you do that, you got an exponential, so it's its own derivative with an ln 0.98 tacked on. Now you plug a 40 into that, and you get negative 450. What would be the units on that?
Per year.
People per year. Is the population increasing or decreasing?
Decrease.
It's a chart question, right? P prime we just found out was negative, so therefore P has to be decreasing. P is the population. So on January 1st, 2000, the population was decreasing at a rate of 450 people per year. Okay. Sometimes that's said in 2000, or on January 1st, 2000, there were 450 less people than there were on January 1st, 1999. That would be a similar way to say it, because you're getting the per year in there by comparing 2000 to 1999. Yes.
Would it be like acceptable use reasonably in this? If it's like less than 1, the power that's being raised, or the number that's being raised to the power?
Yeah, anytime this number in an exponential is less than 1, then it's going to be a decreasing, like an exponential decay kind of thing. They're losing like 2% per year is what's happening, right? As opposed to when it's over 1, it's going to be that, right? So to say the population's decreasing because it's that would be okay, but you still would have had to found this, right? It still said find the rate of change on January 1st, 2000. So you still have to find this number. But from a calculus perspective, I think it's better to say since P prime is negative, the population is decreasing. I like that one better. But you're right, that's also why it's decreasing, because of the type of function it is. All right, let's move on to the trig section now. And the 2.7 homework question. And so the first part of this, of course, we're going from -5 to 5 here, so we can't forget about that. So that was a little different, because a lot of times on trig problems it's 0 to 2 pi, so we had to really keep that in mind. But we were doing, the first question was, are there any stationary points? Yes. And then 12 and 13 was, is there local max or min? Well, those kind of go together when we do a number line. So this is just kind of basic problem we've been doing. I hope it becomes a basic problem for us. So we do the derivative, which is 1 plus cosine. We set equal to 0, you get cosine -1. Now, on it, pretty good bet that you're going to have to do some trig without a calculator on this next quiz. Now, we're going to have a calculator part 2, so maybe that'll be on the calculator part, right? But where does cosine equal -1? Well, cosine's the x-coordinate, so it's over here at pi. But also a negative pi, right? Now, 2 pi is 6.28, so that would be outside of a range here. Okay, so you wouldn't go around any other times. Now, the other thing you could do is when you solve this, again, I don't want to limit you, but normally I think of the unit circle, but right here, where does cosine equal -1? Well, you could think of the cosine graph, right? When does cosine equal -1? At pi and negative pi, right? When does cosine equal -1? It's at pi and at negative pi. And then if it did it again, it would be outside the -5 to 5. So you can solve this any way you want without a calculator. However you want to think about it is okay. All right. Now I went ahead and put that on a number line, picked some numbers in between. I got positives for everything. Put a 0 in here, cosine of 0, we're going to put it in here now. Cosine of 0 is 1, 1 plus 1 is 2, so I got all positive. So that tells me f is always increasing, so that answers 12 and 13 for us. There's no local max, no local min, the function's always increasing, since f prime never changes sign. Remember, if you're going to give a local max min answer, you have to justify it. Well, if there isn't a local max min, you got to tell why. So you might lose points if you don't have this down. There's no local max min. It didn't even say justify, but you better get in the habit of justifying when it's local max min. Never change the sign on F prime, so there's no local max min on F. Okay, so that answers 3 of those 4 questions. The other question was inflection point. We just talked about that yesterday, so let's take a look at it. The second derivative of that 0, derivative of cosine's negative sine. I'll divide by -1 to get it out of there. Where does sine equal 0? Now you can do a unit circle, which would be at 0, which would be at pi. 2 pi's outside the range, but you also could go backwards and have negative pi. Or you could just do a sine graph. Right? Where does sine equal 0? 0, pi, negative pi, right? So there you go. Put those on a number line. Now something interesting here. You got to be careful when you plug these numbers in between. If you pick something that's outside of the range, something bad might happen. Like I tried to put a 2 pi here, because that's to the right of pi. But watch what happens when I put 2 pi in here. Sine of 2 pi is 0. So I don't get a positive or a negative, I get 0. Well, it's another possible inflection point. But 2 pi is outside of my range, so I'm not going to want it. So I had to fix that. I had to say, well, I can't do 2 pi, I better do 3 pi halves. Pi halves, so forth. So let's just do pi halves, for example. So I put pi halves in here, sine of pi halves is 1, but then don't forget about this negative. And this is, I talked about this yesterday. This is my second derivative right here. Okay, that's where I have to plug it. Now I divided by a negative when I was solving it, but so I can't plug it back in here because that'll throw off my sign. All right, so anyway, I get negative here, positive, and so forth. What's this mean about F right here? Concave down. Concave down. So those are inflection points. And you have to have, so here's your answer to number 11. You have to have this. These are inflection points because when F double prime changes sign, F changes concave. Okay? So you've got to have that to get full points for that answer on that. Okay, that's a real basic chart question right there. It's got all the chart stuff in it. It's got increasing, decreasing, it's got concave up, concave down, which tells us inflection points, which tells us local max min. It's everything that's in the chart. Right there. Okay, guaranteed to have one of those, probably one of those on the no calculator part, and probably one of those on the calculator part. And global, don't forget about global max min, probably is going to get thrown in there too, like list of candidates. And we'll be doing some more practice on those too. All right, a couple quick derivative comments here on the trig ones. Of course, we remember we got to kick out a 2 here. Derivative of cosine is negative sine, so we can't forget that. Don't forget the inside never changes, so that's going to stay 2x. What was it, 26 then? Is that right? We had to do the second derivative. Did I do that right? Was it 26?
Yeah.
Okay. Do the second derivative, which means we're going to kick out a 2 again. Derivative of sine is cosine, so we kick a 2 again. That becomes a 4. Okay. And then 32 had to do the anti-derivative. So now we're looking back up at the original. So it was cosine. You know it would have been sine. You know the inside never changes, so that'd be a good guess right there. So you're going to check it, guess and check. So you say, okay, derivative of sine to be cosine. Yep. 2x stays same. Yep. Oh, I got to kick out a 2. There's no 2 then. So there must have been a 1/2 sitting there. There must have been a 1/2 sitting there, so when I kicked out the 2, we had that. And then Joe? Plus C. I thought you were going to remind me that. You forgot it. Plus C. Okay? Plus C on the antiderivative. Now, we're going to, in a second here, we're going to, or not a second, but in a little bit, we're going to talk about why it's so important, where it can really be important, like Cesar, you asked earlier about putting on that plus C. All right, I think that's all I got on the homework. Is that good enough?
Yeah.
It's quite a bit, probably too much for some of you, but.
When you do these, can you leave it as 2 times like negative sine times like 2x?
Yeah.
Say that again.
Like I left mine, I didn't combine them. I left it as 2 times a negative sine of 2x and 4 times a negative cosine of 2x. So then I wouldn't forget. Like,
You did 4 times negative cosine 2x like that.
Like I just left them separated.
Yeah, on this quiz, I don't think I'm going to get real picky about that. When we get to chapter 3, we're going to do a bigger quiz of really doing these derivatives. Then I would say you would have to, because to me, that's like combining a 4 and a -1. I think we should do that. That's -4. So I think we should write it like that. I think it's good to get in the habit, because usually you're rarely going to do the derivative other than a test where they just say do the derivative. We have one of those coming up, chapter 3. This one will have a few of those. Most of the time we're wanting to do the derivative, then do something with it, like set it equal to 0 or whatever. Well, then you're going to have to do that anyway, so you might as well get in the habit. Okay. All right. So don't write this down yet, because later in the week we'll go over kind of a summary of the quiz and what things are going to be on it. But if we just look ahead right now, we've got basically 4 things, and it depends how you want to count them, but that are going to be the main themes that'll be on the next quiz. The first one we haven't learned yet, and that I've listed here, and that's what we're going to talk about next. Okay, this is section 2.5, something called differential equation. Okay. The next thing, another thing we've talked about is global max-min. That's finding the highest, lowest point, list of candidates, that kind of thing. Okay, then you got the chart stuff, which we just went through, problem 10 through 13, which is a great example of all the chart kind of stuff that you could do and how we go about finding that. And then there's just derivatives, finding antiderivatives, which is a lot of what today's homework is about. And of course, all of those parts are going to involve derivatives and antiderivatives, right? Finding derivatives like your chart problems, your global max-min, you got to find derivatives. The new thing we do is going to involve antiderivatives a little bit, not a lot, but it's going to involve derivatives too. So that's it. I mean, that's it, is the big themes of what the quiz will be about. That's it. Okay? All right, so let's go ahead and let's talk about differential equations. So in your notes, you might want to kind of start another page. This is kind of a separate thing here. And in some ways, it's a little bit of a side trip, I guess, kind of like limits were in the last section. Your book kind of tends to organize things that way a little bit, which I actually think is a good thing. Differential equations is something we have to know a little bit about. When you get to the AP test, you get to the end of Calc 1. And so what they do is, as soon as we've learned enough to do a little bit of differential equations, they throw it in. And then we learn another new thing that could apply to differential equations, they throw it in again. And then we just kind of build up our knowledge of differential equations. Okay? So we now, with these derivative and antiderivative rules we've talked about, know enough to just start talking about differential equations. Now, what's a differential equation? Well, if you go to college and have to take a lot of math, say you're going to be an engineer, you're going to take Calc 1, well, you might skip Calc 1 after having this class, go to Calc 2, go to Calc 3. After Calc 3, the next course is usually a course called differential equation, or as
one whole course
called differential equation, or as the math geeks like to call it, DiffEq. DiffEq, that sounds like that. DiffEq. What are you taking this semester? I got DiffEq. I'm in DiffEq. I got named DiffEq. This sounds cool. Okay, DiffEq. But differential equation. All right. Now, what does that mean? Okay, well, think about it. In 8th grade, probably in 8th grade, maybe even 7th grade, you started learning how to solve linear equations. 2x plus 7 equals 5. Remember, especially we were talking about solving, right? The word solve, what's that mean? This is where we solve. We solve equations, right? Solve a linear equation. Then you got into Algebra 1, and then you learned about quadratic equations. So you solve those. Well, you could factor, or you could maybe use a quadratic formula, right? You learned how to solve quadratic equations. And then you got to advanced math, and you learned about log equations and exponential equations and then trig equations, right? You solve these different types of equations. Well, differential equations is another category of equations that you solve, okay? Now, what's word differential mean? Well, differential is another term for derivative, right? When you take the derivative of a function, another way of saying that is different. Sometimes you'll see differentiate this function, right? So differential or derivative, they're kind of interchangeable as terms. So differential equations, so there's 2 main things I want you to know about differential equations, okay? The first thing is a differential equation. Now your book abbreviates that DE a lot, okay? So a DE, a differential equation, is an equation with one or more derivatives in it. Actually in the equation. one or more derivatives actually in the equation. Now, think about a quadratic equation. What do you have to have for something to be called a quadratic equation?
Squares.
It's got to have an x squared in it as the highest power. It's got to have an x squared that's the highest power, and then it's a quadratic equation. A linear equation has to have x to the first as the highest power. Trig equation has to have a trig function in it, right? A differential equation has to be an equation with a derivative in it. If it's got a derivative in it, it's a differential equation. Okay, now, I would suggest to you we've already seen some of those. Okay, for example, and what's the word equation? It's got to have a what in it? Equal sign, right? So it's got to have those two things. So it'd be a differential equation, it's got to have an equal sign in it, so it's an equation, and it's got to have a derivative in it. Okay, if it's got those two things, it's a differential equation. Okay, so here would be, I would say to you, a differential equation, and we've seen this already. Or we've used f prime a lot instead of y, but in differential equations we tend to use y a lot more than function notation. That is a differential equation. It's got an equal sign in it, and it's got a derivative, it's got a prime. It's a differential equation. Okay? All right, second thing I want you to know about differential equation, I will ask you this every time we start talking again about differential equation. I'm going to ask you these two things. Okay? Second thing is the solution, and this is where you really got to get a change of mindset from the equations you've learned up till now. The solution to a DE, a differential equation, is the original equation y equals da-da-da-da-da.
Which is the antiderivative.
Well, sort of. The antiderivative is going to be involved, right? In other words, if you got y prime, do the antiderivative, you get y. That would be an example, but I'll show you why that's not the whole story. Okay, the solution is the original equation. So that's weird, because what's the solution to a quadratic equation? A number, and a lot of times two numbers, right? The solution to a linear equation is a number, right? A cubic equation could have three numbers. A trig equation can have an infinite number of solutions, right? But they're numbers. Not the case here. A differential equation, the solution is another equation. It's the original equation without derivatives in it. It's the y equals. Now, let me give you an example. So, the one I just showed you. So, if we had the DE y prime equals 6x plus 5, then Cesar would be exactly right. The solution would be y equals 3x squared plus 5x plus c. So now think about this. I could ask you a question with this new terminology that would be the same thing you just got done to do in the last chapter, or last night's homework. So instead of me giving you this and say find the antiderivative, I could give you that y prime equals 6x plus 5 and say solve this differential equation. That sounds so much more impressive, right? Solve this differential equation. Well, what you're going to do is you're going to do the antiderivative, because the solution to a differential equation is the original equation y. Okay? Right now, so let's talk about why Cesar's comment about, well, let's just do the antiderivative. If it was that easy, you wouldn't have a whole course, right, in differential equations, if all you had to do is the antiderivative. Okay? So that is one option. So the next page of this that I'm going to put up here is 3 types of DEs, differential equations. Now, I'm going to put a little disclaimer here. I'm going to say, at least for us this year, there are 3 types. If you tonight maybe out and about and run into a UNK math professor and you say, hey, my top teacher told me today that there are 3 types of differential equations, he's going to say, well, he's an idiot. Well, he might say that anyway, but he's an idiot because there are way more types of differential equations than 3. I mean, in our class for this year, we're going to categorize it into 3 different types of differential equations. Okay? First type would be the one we just talked about, and Cesar would be exactly right with his analysis of that. The first type is DEs that we can solve by antiderivative.
Say equals.
So let's do a couple of examples. So one would be the one I just wrote down. Y prime equals 6x plus 5. The solution to that would be y equals 3x squared plus 5x plus c. Okay? Easily solve that one. Another example, let's use p prime this time. It doesn't always have to be y. Right? It could be like that population example we did. Population, p prime equals 3 to the t. Right? Well, then the solution would be p equals what? 3 to the t. Yeah, not ln3 because that'd be the derivative, right? We're doing the antiderivative. So this means there must have been a 1 over ln3 setting there. So when we check it, do the derivative, we tack on an ln3 and it cancels. And then plus c. Okay? Now, or actually, and then the easiest one of all, what if you just had y prime equals 7? Then y equals 7x plus c. Now, here's the problem with that one. If you just have y prime equals 7, how do you know the input variable's x? How do you know it's not t or something else? Well, you wouldn't know. Unless they said y prime of t, then you would know t is the input variable. And sometimes they do that. Sometimes they say y prime of t instead of just y prime. I think it's just extra notation. I'd rather not have in there. But at least it tells us it's a t. So we wouldn't know if this is an x or a t or whatever. Okay. Sometimes it's t with differential equations because a lot of times they have to do with time, and so t is a good variable to use. Now, what do those all have in common? What they all have in common is it's got a y prime by itself on one side, and it's got just x's or t's on the other side. If that's what it looks like, where it's just a y prime on the left and x's or t's on the other side, then we can just do antiderivative, and that's fine. Okay, but there are two other types that we're going to run into. Yeah. Another type are going to be DEs that we can't solve but we'll memorize the solution. Now there's only going to be two. There's only going to be two, and we're only going to do one right now. So it's not that big a deal. But here's the one we're going to memorize. So y prime equals k times y. So that's the DE, right? That's the differential equation right there. Now what's different about that one? It's got the y prime on the left, and it's got y in it. It's still a differential equation. It's an equation. It's got an equal sign, and it's got a derivative. So it's a differential equation. Problem is it's got a y over there, not an x. And we know, and that's the output variable, right? We want the input variable over here, the y prime here, and then we do antiderivative. We can't just raise that up to a 2, right? We can't do our antiderivative rule on that. We can't just raise that up to a 2. That doesn't work. When it's the output variable, doesn't work. So we can't just do this by doing an antiderivative, okay? So we're just going to memorize the solution to that. And the solution to that is y equals, because that's always what the solution is, right? It's always the original equation y. So it's y equals ae to the kt. Yeah, and it's like, where did that come from? How was it that? Well, you did this in advanced math, didn't you, like compound interest? Yeah. This exponential function equation. Okay, that's why it's such an important one. That's why we're going to memorize it. Now, let's think about that in terms of that compound interest scenario. T would be the time that it's invested, and Y would be the amount of money in the bank, let's say. So Y is amount of money, Y is dollars. So what would Y prime be then in units? Dollars per year. It'd be the increase in your account, how much your account is increasing, right? So y would be the amount of money. So k is just some constant of proportionality. So you probably heard about this in science. You've talked about this before in science class. Direct proportion. What this is saying is that y prime, the rate of change, is directly proportional to the amount of money that you have. In other words, it's like saying that the money is going to grow at a higher rate when there's more money in there. Well, that makes sense. If you're getting 6% interest, if you have $100 in there, after a year, you'd have $6. I mean, if we're just doing simple interest. If you had $100, you'd have $6. Your money would grow by $6. But if you had $1,000 in there, your money would grow by $60. If you had $10,000, it would grow by $600. So your money's going to grow higher, faster. Now, not by percent rate, but by dollars per year. You're going to gain more dollars per year the more money you have, right? So that seems reasonable. Seems like that. So here's the advantage of differential equations, is we can talk about situations that involve rates very easily with differential equations. The downside to differential equations is, what if, okay, great, my money is growing at a rate proportional to the amount present. Good. But how much money do I have after 10 years? There's nowhere to plug a 10 in. This is much easier to work with if I actually want to know how much money I have after a certain number of years. So the solution to the differential equation is what you want to work with. The solution, the differential equation can easily describe the scenario, but to actually find out information about the scenario, you need the solution to the differential equation. That's why it's valuable to be able to solve it, and that's why you have a whole course in doing this. Later this year, we'll learn how to solve this, but we don't have enough information to be able to do that this year. Okay? All right, the third category is DEs.
Well, what's the other one we have to
We're not going to do it yet. That'll be later. So the third scenario, the third type, are DEs that we can't solve,
No solution.
but we can check, or I'm going to put in parentheses, verify, if something is a solution. Okay? We can check to see if something is a solution. For example, my Algebra 1B class, we just learned this, we're solving quadratic equations right now. Okay? Well, a month ago, they didn't know anything about solving quadratic equations. And to be honest, right now they don't know a heck about it. But if I gave them a quadratic equation, right? If I gave them this and said, is x equals 5 a solution? What would they do?
Stick it in.
They would just plug it in, right? So you don't have to know how to solve this to check to see if something is a solution. I can just plug in a 5. Okay? And it turns out it is, right? Okay?
It'd have to be.
Oh, it'd be negative 5. No, it wouldn't. It'd be 5. Oh, yeah, you're right. Yeah, I got my negative backwards. I was trying to come up with one that would work here. It was minus. All right, anyway. See, that's why they can't solve it. Their teachers ain't. All right, so anyway, so we got the same thing. Now, here's where you could get into all kinds of crazy looking differential equations. For example, here'd be one right here. Y double prime minus x squared equals 3y prime plus 4x, right? That's a differential equation. It's got an equal sign, and it's got one or more derivatives in it, right? The solution to that would be y equals something with x's in it, right? Well, now, couldn't we check this? Like, for example, if I said to you, is y, now remember, the solutions are not just numbers now on differential equations, they're actual equations. So I could ask you, is y equals x squared a solution to this? Couldn't we check it? Well, what would we put right there? we would substitute in, right? Just like I just showed you. So what would we put in for y prime?
X squared.
Not x squared,
2x.
because that's y. Y prime would be 2x, so we put a 2x right there.
I'm stupid.
And what would we put in for y double prime? 2, because that'd be the second derivative of x squared. So we'd put a 2 right there, we'd put a 2x right there, and we'd see if they're equal. Well, it turns out they're not, because that'd be 10x, and this would be 2 minus x squared. Those aren't equal. 2 minus x squared is not equal to 10x, right? So we would say, no, y equals x squared is not a solution. Okay, and we're going to do some of that today. There's going to be somewhere it's going to say verify that this is a solution, or is this a solution, yes or no, or something like that. We'll do an example here right now. Okay, but we could do that. But you got to think about how we would do it if it was just algebra class, right? Is x equals 5 a solution to this? Well, plug in a 5 and see if it's equal. Is y equals x squared a solution to that differential equation? Well, plug in an x squared everywhere you see a y, because there could have been some y's in here. So plug x squared everywhere you see a y, plug 2x everywhere you see a y prime, and plug 2 everywhere you see a y double prime, and then see if the two sides are equal. Okay? So we can verify, so even if we can't solve the differential equation, we can verify if something is or not. All right, so let's do a quick example. One of your homework problems, I want to warn you about this because people get confused about it. Sometimes I forget. We're going to go through one of your homework problems together here in a second. So if you've got, what do we get? Okay. It gives you this in your homework. It says y prime equals that. Now, how would you read that? Yeah, I think a lot of people read that as 1/2 y. Well, it's not supposed to be 1/2 y. It's supposed to be that. It's supposed to be 1 over 2y. Okay? And the same thing, there's another problem that does this. Well, it's supposed to be that. Okay? So just for your information. All right, so let's go ahead and do this. This is going to be one of your homework problems. This is number 5 on page 129.
Should this be in like our notes too?
No, it doesn't have. Well, it could be in your notes. You could, if you'd rather put this in your notes and then copy it over to your homework, that's fine.
This is gonna be the first question on our homework.
No.
Dang it.
Why you gotta do this?
Oh, geez. 3 and 4 will be the first ones.
Okay, how much space do we need?
Jeez, you guys are a little too picky about it. It's good to be neat with it. That is true. But all right. So on page 129, number 5, it says, is g of x equals square root of x plus 4? It said, is that a solution to this differential equation right here? And this is one of those where it writes it weird. And then it says justify your answer by differentiation. See example 2. Well, though, I mean, justify your answer by differentiation just means you're going to use the derivative somehow. And that's what we want to do. To see if this is a solution, we need to plug something in for y and something in for y prime to see if it is. Now, they confuse you a little bit too by calling that g of x. Well, that's the same as, just call it y. Okay, that's what they mean, right? They could have, because they could have written this differential equation as g prime of x equals 1 over 2 g of x. So you see how all those parentheses and x's just makes it more confusing? Those two are the same exact thing, okay? So they could have written it like this. So for g of x, we would do this, and then g prime of x, we would do that. So I don't care. You can do either one. I would just leave it, right? Just know y is your output, g of x is your output. They're interchangeable. Okay? All right, so we got this. So the question is this our solution? Right? That's the question. Now, sometimes people get confused here because there's two equations. There's an equation here, there's an equation here, and they're kind of which one's which. Well, remember, the differential equation is the one with derivatives in it. The solution is the one that's just y equal. And again, just to remind you, if I had x plus 4 equals 10, and I ask you, is x equals 8 a solution?
No.
Now, that's so simple that we can just do it in our head and don't have to write much down. But let's say you were back in 4th grade or 3rd grade or something, and the teacher was making you really, show all your work and do all this stuff. you might do it something like this. Now, this is just a suggestion. You don't have to do it this way, but you do have to clearly show that it says, is this a solution to this? Yes or no is not good enough. I want to see clearly by your work that it's yes or no. So I'll show you what I mean. Well, I'm going to show you on a real simple example so you can kind of get the idea. I call this a T chart. If I was going to check to see if 8, because it kind of looks like a T, right? If I was going to check to see if 8 was a solution to this, I would put an 8 right here. 8 plus 4 is 12. Does that equal that?
No.
No. And I would say, no, it's not a solution. Because we can see very clearly that this side does not equal this side. Okay? And I put the line there because it's not like we can cross over. We're not solving anything. So we're not subtracting from each side. I don't want you solving it. Remember, the whole reason we're doing is x equals 8 a solution is because we're looking at problems we don't know how to solve. Right? So don't say, well, just solve it and see if it's 8. No, that defeats the purpose. We're talking about doing this on problems we don't know how to solve. So we got to pretend this is one we don't know how to solve, but we do know how to add. Right? So we do know how to add. Well, same thing here. We do know how to do derivatives. We just don't know how to solve this differential equation. So we put an 8 in. 8 plus 4 is 12. No, clearly it does not equal that side. So we got it. Well, that's what I would do in this problem. I would come over here and I would do this. I just think this is a really nice, clean way to show if it is a solution or not. You don't have to. You can do your derivative, have your work, and if it's clear enough to me that I can tell, then you'll be okay. The danger is, will it be clear? All right, so over here, where do we put for the y? Radical x plus 4. What do we put for the y prime? Well, we got to do the derivative of this. That's why it says justify your answer by differentiation. They're telling you you're going to have to do a derivative. So I need to do y prime. Well, this is x plus 4 to the 1/2.
Yep.
Remember how we talked about how you write it is going to be key to doing the derivative? So y prime is what? 1/2 down in front. Always leave the inside alone. See, so we're getting some practice with our derivatives while we do this. No, because it's not times the x, right? The plus 4 just shifts the graph left, and that doesn't affect the slopes other than shifting. No, if it's times. If it was like 2x. Yeah, if it's like 2x. What do you need? Thanks.
Okay, good.
Oh. That's the wrong room. She's just around this corner by the bathroom.
Hunter.
Over by the bathroom. All right. So that's the derivative right there. So we're going to substitute that right here for y prime. Right? So we're just, now again, it's just like I said back on this other page. Right? If y equals x squared was our solution, we'd put an x squared everywhere there's a y. We'd put a 2x everywhere there's a y prime. And we put a 2 everywhere there's a y double prime. Well, this problem, everywhere there's a y prime, we're going to put that. Everywhere there's a y, we put that. Now, are those two equal?
Yep.
But it's not good enough to stop there. Because it's just like here. I couldn't stop right there with 8 plus 4. Does 8 plus 4 equal 10? No, I need, we need to be able to have, somebody who doesn't know anything about math look at it and say, oh yeah, those two are equal because they're identical. So we need to show that these two are identical. So flip that around, that will go to the bottom, and then it would be square root. And so then, now if you could tell just by looking at it, yep, I flipped that, that'll be it. Just write it, that's fine. But now we can look at that and we can say, oh yes, for sure. Those two are identical. So yes.
Does it matter which side we do that to?
Nope. What do you mean? Like if you took this side and rewrote it so it looked like that side, that's fine. We just want the two sides to be equal, that's right. You could, yeah. So like on this problem, well, you could really do that with work on this problem. Anyway, okay, so there is your verify. A lot of times they use that word verify or show that this is a solution or is not a solution or whatever. Okay, so you're going to have several of those kind of problems today where you're doing that. Okay? All right, so that's it with differential equations. Most of your work is going to be here in this verify kind of thing. You might have a few where you can just do the antiderivative on that. Okay, but that's just getting us introduced a little bit to the idea of differential equation. Why are we doing it now? Because it involves doing a derivative and an antiderivative a little bit, which is what our homework was on yesterday. Plus, section 2.6 is all about exponential equations, and one of the most famous differential equations is this one right here, which is exponential growth, right? Exponential growth and decay is that differential equation. All right, let's do one more problem that's part of your homework. I'm actually going to change this a little bit because I did this for the other class since they got cheated out of some of their time, so I'll help you guys out too. Since I guess, how many people had first block off? Anybody? Oh, okay. So you guys all had to stand out in the cold?
Yeah.
All right. Okay, then I don't feel bad helping you out. Okay, so I'm going to change that to, actually, I said this is like number 37. This actually is number 37, okay, which is on your homework. This is on page 147. I'm actually changing what's on your homework sheet a little bit, so.
So does it go from 5 to 37, please?
What?
Is the next? The one
No,
that's 5?
no, 37 is not the next problem, no. Not even close. Okay? Now, matter of fact, everybody turn to page 147. I want you to read these directions here. Okay? Page 147. So, they give you this function, and it says, so I'm going to change the directions here on a little bit. Don't draw a graph. Okay? It says draw a graph of the function over the interval 0 to 2 pi. Label all local extreme and global extreme and points of inflection with both coordinates. What am I going to do? Okay?
It's just like our homework.
I wanted to do it more like our homework. So we're going to do local max min. It did say inflection point, so we're going to do that. So there's plenty to do here. And then when you do a list of candidates, you're going to have to plug those, to do a global max min, you're going to have to plug those back into the original. So you're going to get both coordinates on those points anyway. So you're going to do most of that. But we used to, and this book kind of is going back to those days, before graphing calculators, so this is how long ago I've been around, but before graphing calculators, we used to do a couple week unit on just sketching graphs. Well, if you think about it, we're doing most of that anyway. But once we find the local max mins, the inflection points, all that stuff, all we have to do is then plug those back into the original and plot them, and you pretty much know the graph, right? Because you know when it changes concavity, you know when it's going up, when it's going down, where its peaks are. And we would sketch really careful curves and really have to draw. We're not doing that part of it anymore. That's kind of what this is saying. So you don't have to draw that graph part. So right now I'm just going to focus on, I wrote global max min, but we'll do a number line too, and then I'll let you just work from there. But where do we start with a problem like this then? Start with the derivative, set it equal to 0, right? So here we go. So the derivative is 1/2. No. So, okay. Glad you asked that. So when we go back to the 4 things I said would be on the quiz, differential equations is kind of this one that's off by itself. Now, when you verify, like that T-chart, you're going to have to be able to do a derivative, right? So there's that connection, right? But that's something totally separate. Finding the global max min, the chart kind of stuff, that's separate, right? So that's 2.6, 2.7 sections doing that kind of stuff. Differential equation is a different scenario, okay? All right. Related, but this isn't a differential equation. All right, so then we get what? Plus cosine x equals 0. Okay? I mean, I guess if you wanted to get really technical, this line right here is a differential equation, right? This line right here is an equation with a derivative. But so what? That's not what this problem's about, okay? All right, so we get to there. Don't forget set equal to 0. So cosine x equals negative 1/2. Now here's where, you know, I have to do this all year long, but I've said if you don't know your trig values, if this is a no calculator, which this one would be, right? You're gonna be kind of stuck here, and then you can't get your number line, and you can't answer the question. You could potentially lose a lot of points if you can't solve that. Okay, so between now and Monday, if you're still having problems with that, I got all kinds of trig review stuff online. Whatever, come in, talk to me, whatever. But what is the answer to this?
2 pi over 3.
It's 2 pi over 3.
4 pi over 3.
4 pi over 3. Now, the fact that not everybody shouted that out makes me think there's a few questions. So here's how I would have went about doing that. Okay, you go to the unit circle, right? Now this lower one, remember, our important values are 1/2, square root of 3 over 2. Square root of 3 over 2 is like 0.8 something, 1/2 is like 0.5. So the low angle here, pi 6, remember that one's 1/2 and root 3 over 2, like that, right? Okay, so that's pi 6, right? Cosine is the x-coordinate. Cosine would be root 3 over 2 at pi 6. At pi thirds, right, it's the other way around, right? The short leg is the 1/2, and the taller one is root 3 over 2. Okay, so the cosine is 1/2 at pi thirds. But where is cosine negative?
Quadrant 2.
In that quadrant, Because remember, cosine is the x-coordinate on the unit circle. So the x-coordinate is negative here and here. Or you do the cast thing, or however you remember that. Okay? That was cast. It was C,
No, it was C-A-S-T.
A-S-T-C, like that. Right? So all of them are positive here. Sine's positive here. Tangent's positive here. Cosine's positive here. Okay, so negative. So cosine's negative over here. Okay? So in these two quadrants, so you got pi thirds as your reference cycle. So that'd be 2 pi thirds, and that'd be down here 4 pi thirds. Okay? You just gotta know those values. All right. Now we're talking about between 0 and 2 pi. So those are my stationary points. Okay, so that's where my local max min is going to be, that kind of stuff. So let's go ahead and just do that. So we got f prime. We got 2 pi thirds. We got 4 pi thirds. Now, it's possible that if you get the wrong values here. So for example, let's say you put pi thirds and 5 pi thirds. Or let's say you put 5 pi 6 and 7 pi 6. You thought it was pi 6 in these two quadrants, right? So you got the wrong values. So then you put those on the number line, you plug them in, you get some other stuff. It's possible that if you go forward, and they do a good job of this on the AP test as well, if you have a wrong answer there, of course everything else is probably wrong after that. But if you take your wrong answers and you do some right stuff with them, it's possible, not guaranteed, but possible you could earn a point or two in some later steps. Possible. No promises, but so if you can't find those values, it doesn't mean you just quit, right? You never know. All right. So anyway, what are some values here? Well, 0 would be between here, pi would be between here, 2 pi would be here, and we're going to plug those right back up here into our f prime.
Wait, you said it wasn't global.
It did, but it did say local also. So
Local also.
in the directions it did. The directions said local, global, and inflection points. Local, global, and inflection
Does
points.
it give us a 0 to 2 pi?
And it gives us 0 to 2 pi. So for local max and min, we'd be doing this, right? So we put a 0 in. Cosine of 0 is 1 plus a half, so that's positive. Cosine of pi is negative 1. So 1/2 plus negative 1. 2 pi, cosine of 2 pi is 1 again. Okay. So I'll let you finish that part out. List of candidates. So Joe was saying it said to do global max and min. So that means we take our stationary points, plug those back into the original, and we take what else?
The endpoint.
Interval.
We take the interval endpoints and we plug those in. Now, here's where it gets a little bit, I want you to go ahead and try this without your calculator. It gets kind of messy here because just think about this first one, 2 pi thirds. You gotta plug that into the original. You have to take 1/2 times 2 pi thirds. What's 1/2 times 2 pi thirds? No, 2 pi sixths, which would be pi thirds, right? Or 1/2 times 2 pi thirds is gonna be pi thirds, right? Plus sine of 2 pi thirds. What's the sine of 2 pi thirds? Root 3 over 2, right? Sine of 2 pi thirds is gonna be positive root 3 over 2. So what you end up with for this one is pi thirds plus root 3 over 2. Now remember what you're trying to do. What are you trying to do with your list of candidates?
Find the highest.
Find the highest and the lowest value. So you got to have a little bit of an estimate of what that is. Now, it's possible, not likely, but possible you could have to do this on the quiz. But on the AP test, this could come up in some problems for sure. Well, what is that? Well, we can estimate that pretty close. Pi divided by 3 is about 1. Root 3 is about 1.7 divided by 2. That's actually a value you should know anyway. Root 3 over 2 is 0.866. Root 2 over 2 is 0.707. All right, those are just some values that would be good to know. Okay, well, I know, but I just told you, so now you should know. I just told you.
Oh, for the rest of my life.
For the rest of your life.
A little bit above 8.6.
So this is about 1.8 or 1.9 roughly, right? A little over 1 plus 0.866 would be about 1.9, be pretty close. Okay? And then likewise for the rest of them. Okay? Likewise, now if you get a couple of those that are so close together, you're really nervous about it, then grab your calculator, look at it, whatever. It wouldn't hurt to practice this one with your calculator also. Okay? Do a solve. Remember the vertical bar? Solve, vertical bar with, we're going to do some more calculator ones later this week, but do a solve, vertical bar, that kind of thing. So there's your global max min stuff. Your local max min stuff's all in your number line. Now what's left for you to do some inflection point, right? Which you need what for inflection point?
Second derivative.
Second derivative, because inflection concavity is told by the second derivative. So you're going to do the second derivative, set it equal to 0, do your number line. Okay? All right. So right there, in those
That's really close.
2 problems we just did, are a big part of what we're talking about on the quiz, to be honest with you. Verifying on these difference equations, but we need a few days to kind of let that soak in with difference equations a little bit. And we just need some more practice, both with our trig and just this local global max min. But I don't have a whole lot new to tell you between now and Monday, to be honest with you. I've thrown a lot at you for 3 days, but it's going to be a lot of review and practice problems and so forth as we go along. Okay? All right, so the homework. Go ahead and grab that assignment sheet.
I said I could throw it out.
Well, I did, you're right. So if you threw it out, then you're in trouble. You never should have listened to it.
Instruction.
Okay? So you can just write these down then if that's what you did. So right down here on this line here, the first, okay, on this one right here, we're going to change a couple of things. Not much. Instead of this 6 right here in the beginning, we're going to make that 3 through 6. Okay, we already did number 5. You can cross off, since I added, we'll make it fair. We can cross off number 43 at the end. No.
19.
No.
That's like
Cross
they're
off
equivalent.
everything.
And 37 is the one we already did, like half.
On ours, it says
Okay.
39.
What's that?
On ours, it says you want us to do 39, not 37.
Oh, it does?
Mine anyway.
It's just,
I printed it off on,
out.
I can't.
Oh. Have they been wrong? Have they ever been wrong on this? Yours says 39. Is anybody else that say 39?
I guess we'll just throw that out.
Printed it off.
Because they were all here. We'll just throw 37.
All right. Well, cross off the 39 and make it 37. Okay? If yours said 30, how many else, Devin, yours say 39? No, anybody? Huh, that's weird. You printed off the website, so I obviously uploaded the wrong one. Okay, all right.
In the group chat.
Can't believe I would do this. All right, so, now, remember what the section was. So 2.5 was the section on differential equations. Okay, so those are gonna be the ones like verify, is it a solution, something about the differential equation, that's a new thing. 2.6 was the exponential function. So there might be some differential equation stuff in there. Right, about the e to the x, that e to the kt kind of thing. And then the last one were the tricks. Yeah, cause we're on that different schedule because of pep rally.
What time?
So third block will start at 1:40, so basically all your lunch times are just 10 minutes. Lunch times are just 10 minutes earlier than they were before. So when'd you go before, 11:50? 11:25, so you go at 11:50.